Welcome to Study Loop.
Once again, welcome to a new problem. This time we're given, this is the information we're given. We're given a bullet that's moving towards the right. This is the bullet and it's traveling towards the right. The mass of the bullet, which I'm going to call MB, happens to be 6 grams, and I'll change that right away to kilograms. So 1 kilogram over 1,000 grams, and that gives us 0.006 kilograms. That's the mass of the bullet that's moving. It strikes a stone. So, there's a stone right here. The bullet strikes the stone, and something happens to the bullet. It turns perpendicular at an angle of 90. Okay, so this bullet now is moving at 90. I should have done that like that. So it strikes the stone and it's moving at an angle of 90. The initial velocity of the bullet, happens to be 350 meters per second, and the positive x direction is that to the right, and then we also have the positive y direction, that's upwards. We do have the final velocity of the bullet, which happens to be 250 meters per second. Now we can talk about the stone. When the bullet strikes the stone moves at a specific angle, theta. We need to find what theta is. Okay, so we want to find theta. And then the other thing that happens is that the stone is now moving with a certain velocity. It's moving with a certain final velocity. So the final velocity of the stone, which we're going to call Vs, is something else we're going to be looking for. So find theta and also find the final velocity of the stone. We don't know what theta is. We do know that the mass of the stone happens to be 0.100 kilograms. That's the mass of the stone. The surface is frictionless, so you want to remember that, not being affected by friction. The initial velocity of the stone is 0 meters per second. Okay, so that's the information we're given, the initial velocity of the stone. And so in part A, we want to find the magnitude and direction of the stone. And then in part B, we want to find the if the collision is perfectly elastic. Okay, we want to find if the collision is perfectly elastic. So, this is all the information we're given. In the next page, we're going to use the law of conservation of momentum. Okay, and that's going to help us find the final velocity of the stone. So, law of conservation of momentum says that initial momentum is exactly the same as the final momentum. So I'll say Pi equals to P final. The initial momentum, that's the mass of the stone. So the initial momentum of the stone, of the bullet, plus the initial momentum of the stone equals to the final momentum of the bullet plus the final momentum of the stone. That's the information we have. Remember, the initial velocity of the stone is zero right here. This initial velocity is zero, and therefore we don't have any initial momentum for the stone. We just have the final momentum. Um, in terms of variables, now we can move stuff. If we move this one to the right, we end up having the mass of the stone and the final velocity of the stone being equal to the initial momentum of the bullet minus the final momentum of the bullet. And so the final momentum of the final velocity of the stone is the mass of the bullet, the initial velocity minus the final velocity of the stone, all over the mass of the stone. So this is the information that we have right now. Going to the next page, we get to see that plugging in numbers, we have final velocity of stone equals to mass of bullet over mass of stone. Mass of bullet was 0.006 kilogram over the mass of the stone, which is 0.100 kilograms. So we've taken care of that. And then also we do have the initial velocity of the bullet, which was given as 350 meters per second I hat plus zero j hat, because it's not moving in the x or the y direction, and then we're subtracting the final velocity of the of this sorry the final velocity of the stone. So we have to change this a little bit. Let's just go back. So we have 350 meters per second I hat, and then we're going to subtract 250. Yes. We have to subtract 250. So this one has to go back. We have to subtract minus 250 meters per second j hat. Remember, I hat and j hat is, since I hat it's in the x and then j hat is in the y direction. That's how it's bouncing off. So when we simplify these numbers, 350 will get 0.006 divided by 0.1. So this is 0.06. It's a factor. 350 meters per second I hat minus 250 meters per second j hat. We use the distributive property for this problem, and so we end up having 21 meters per second I hat minus 15 meters per second j hat. That's the final velocity in terms of I hat and j hat. But remember, they wanted the magnitude and direction, and so we have to change. Finding the magnitude of the final velocity, it's just the square root of the x component and the y component. So this is a square root of, to have some space right there. We need some space. So this is the square root of 21 squared, 21 meters per second I hat squared, plus 15 meters per second j hat squared. Okay, so those are the numbers we have, and then we end up getting a magnitude, final velocity, the magnitude of the final velocity being equal to 25.6 25.8 meters per second. That's just the magnitude. Now we need to find the direction. To find the direction, remember it's going that way, so we have an x component and a y component, and this is the stone. So theta is the tan inverse of 15, which is the x, 15 meters per second, j hat, over 21 meters per second, I hat. Okay, that's the information that we have at this point, and we're using that to find the angle. So theta happens to be 35.5 degrees. So our theta angle is this one right here, and it happens to be 35.5 degrees. In the next page, we want to check. So this is part B. Is the collision perfectly elastic? So that's the question we're asking ourselves: is the collision perfectly elastic? If it's perfectly elastic, then the initial kinetic energy will be equal to the final kinetic energy. So we want to get the initial kinetic energy of the system, and that's 1/2 mb vb initial plus 1/2, this one is squared, ms vs initial squared. Remember, the initial velocity is 0, so this whole thing will be 0. And when we plug in the numbers, we get 1/2 mass of bullet, 0.006 kilograms, and then the initial velocity of bullet, 350 meters per second squared, and that's going to give us 367.5 joules. That's the initial kinetic energy. In the next page, we want to find the final kinetic energy, which is 1/2 mb vb final squared plus 1/2 ms vs final squared. The mass of the bullet is 0.06 kilogram. The final velocity of the bullet is 250 meters per second, if you can recall. We want to square that, and then plus 1/2 mass of stone, 0.001 kilograms, and then times final velocity of the stone, which is 25.8 meters per second. We want to square that. If you plug in the numbers, you get 187.5 joules. And therefore, we're going to say the initial kinetic energy, which happens to be 367.5, is not equal to the final kinetic energy, which happens to be 187.5 joules. And so we say the collision is not perfectly elastic. Hope you enjoyed the problem. We had a case where a bullet was fired towards a stone. It bounced off at 90, and the stone bounced off at an angle. We wanted to find the angle of bounce off, and we also wanted to find the magnitude of the velocity of the stone when it bounces off. We use the law of the conservation of momentum to isolate the final velocity of the stone. We have to remember that the velocities have to be treated in terms of unit components, so the x and the y. And so that's what we did. We ended up using square root and the uh, Pythagoras theorem, comparing the sides of a triangle. And then we got the magnitude, which is 25.8 meters per second. We went again and got the angle using tan inverse, which is 35.5. And then checking if the collision is perfectly elastic, we checked the initial velocity of the system, or rather the initial kinetic energy of the system, which is 365.5. Compare that to the final kinetic energy of the system. They're not the same, so the collision is not perfectly elastic. Hope you enjoyed the problem. Feel free to send any questions and have a wonderful day. Okay, thanks. Bye.